The following podcast is a proud member of the Blue Collar Roots Network. Find all the shows by visiting bluecollarroots.com. Think of this show in this way. Rush Limbaugh and Howard Stern had a child, and that child grew up to have a podcast about building science. This is the opposite of that. Here's Bill Spohn.
Welcome back to another episode of the Building HVAC Science Podcast. We're returning to a topic we've covered before a couple times, a topic near and dear to my heart. It's about the SpohnHome. The construction's finished. Mairlyn and I moved in many months ago. What's it been like for us living inside these theories for a high-performance home? Were there any late-course corrections necessary? Are there any regrets that we have? Well, in this podcast, recorded in April 2021, our friend Allison Bailes, the Energy Vanguard, I suggest you check out his website, energyvanguard.com. He comes on and is host and interviews and investigates if the SpohnHome is truly a high-performance home. We meander off in our discussion and exchange thoughts on a variety of topics, including, does a house need to breathe? Is air a bodily fluid? What are mean or maybe nice radiant temperatures and the impact on naked people? How about some various proven and some sketchy means for improving indoor air quality, our favorite and reliable sources for information, and what's a Comparetto cube? And of course, much more as we get into the conversation. I'll also be sharing updates on what it's like living inside my theories. If you want to learn more about the project, you can go to SpohnHome, SpohnHome.com, and learn more at the blog. Okay, let's listen in as Allison and I share our thoughts on SpohnHome. Is it truly a high-performance home? Today, we're pleased to have with us Allison Bailes from Georgia. How are you doing today, Allison?
I'm doing great. Hey, Bill, how are you?
Great. We're going to talk today a little bit about high-performance houses, and Allison's got some upgrades going on in his house, and I've got a recently constructed modular home. We're going to explore some different topics there. And first, I want to learn a little bit more about what you've done to your house.
Where should I start? Well, let's start at the beginning. I bought the house 2 years ago. Next month, it'll be 2 years since we bought the house, and it's a 1961 ranch-style house with a basement and crawl space. It had a furnace and air conditioner when we moved in, a natural draft gas water heater. It did have an encapsulated attic and encapsulated crawl space, so the air tightness was better than it would have been before. But the attic was in horrible, horrible shape. The spray foam contractor did a terrible job on it. There were some places where the foam, open cell spray foam, was only 1.5 inches thick, which is like our 4.5, maybe, our 5 at best in some places. And the rafters were not covered, so the attic would get hot, it would get humid. So one of the first things I did, I had more spray foam put up there, more open cell. So we're now at R40 minimum, I think, everywhere, and more than that in some places. And it dropped the air leakage significantly. The blower door test it dropped the air leakage about 1,400 CFM50. Not only was it not insulating well, for a spray foam attic, it wasn't air sealing nearly well enough. We did that, and we got rid of the furnace and air conditioner, but that was after we put in the Mitsubishi mini split heat pump. We've got a single unit with 2 air handlers in the encapsulated attic now, and I designed the whole system. It's the 2 low static air handlers rated for 0.2 inch of water column, and we are running at about 0.14. So there's room for a dirty filter and bad fittings if we want to change out good fittings with bad ones or something like that. So happy about that.
So we jumped right in to this, and I need to back up in case people listening aren't familiar with your background.
Oh.
We just assume like we're having a conversation here, like we do know each other, but maybe everyone listening doesn't know who you are.
Okay. My name is Allison Bailes, and I am not a woman. I'm not of the generation that normally does this, but just recently in my personal Twitter profile, I put he, him, and gosh, that would have saved me a lot of trouble over the years if I had been doing that for the last 40 years or so. But anyway, my personal Twitter profile now reads, the first line is, "You know this world is killing me." And for people of a certain generation who remember Elvis Costello and the song Allison,
Oh, right.
There's that line. I know this world is killing you. I'm not going to sing it because I can't sing. But so my background is physics. I've got too many degrees in physics, including a PhD from the University of Florida, 1998, where I studied things that have no real bearing on what I do now. I went deep into one subject, and it turned out, I think, to be a dead end, the stuff I was working on in grad school. But that's what science is about. You explore.
What life is about sometimes. Yeah.
Well, that's true too. So 20 years ago, I bought land, I built a house, and that launched me into the world of building science. I left academia in 2004. I had a company at first doing HERS ratings, manual J's, and then I got into contracting, had a box truck and a cellulose blower and encapsulated crawl spaces. There's several houses in the Atlanta area whose crawl spaces have been encapsulated by somebody with a PhD in physics.
It seems like there should be like an emblem or a logo or a badge of some sorts there. Yeah.
I should have done something with that. Anyway, the company I have now, Energy Vanguard, I started in 2008, and we do. At first, I didn't know if I was going back into contracting. I actually did a couple more crawl spaces, and then got into more training and consulting and full-blown HVAC design. And we were doing HERS training, and we were a HERS QA provider for a while, but we got out of that. So I do speaking, and I write a little blog you may have heard of called the Energy Vanguard blog. And I write
That's an awesome blog.
Yeah, and twice a month I have articles at Green Building Advisor as well. So that's my background.
Anyone listening, Energy Vanguard blog, just solid information, variety of topics in building performance, building home construction, IAQ. I mean, you really revolve around this whole industry. It's really nice, and they're bite-sized chunks, which have references, and they're funny. For a physicist, you're funny.
Oh, thank you. Thank you. Yeah.
Humorous.
Not everybody gets my...
Because funny could be interpreted two different ways.
Not everybody gets my sense of humor. Like about 4 years ago, I wrote an article called 61 Things We Should Ban from New Home Construction. I recently reposted that article on LinkedIn and Twitter and Facebook, and it's amazing how some people thought I was mostly serious about it, including banning thermostats and, and occupants.
Yeah, it's one of those things, make sure you read it till the end.
That one was very tongue-in-cheek, and it was not an April Fool's article. With my April Fool's articles, when you read it, make sure you look at the date.
So let's explore a little bit about the topic here. Do I have a high-performance home? Actually, when I started to talk more about what we're doing here, this house that we built, modular construction, I changed it from high performance to personalized performance, because I thought that the definition of high performance has so many different meanings, and personalized takes that all away. And it's about what the owner, what the occupant wants, and that can vary quite a bit. So why don't you ask me a couple questions, if you don't mind?
Tell me what makes your home a personalized performance home instead of a high performance home. Tell me more about that.
A lot of times people have these loading order or weighing factors as to what prioritizes in front of something else. And one of ours was aesthetics. We would compromise some performance factors in physics or building science for aesthetics. For example, a fairly complicated roof structure that would not pass muster with a passive house type viewpoint.
And complex roof lines were one of the things that I proposed banning
Yes.
in that article.
And that's when I started to squirm when I read it, both times. And from the physics standpoint, which you can certainly relate for our listeners, but it's all this extra surface area for something that looks nice or looks like something else. And then at the extra material and effort to make it perform better. There's a trade-off there. So that was one of the personalized performance.
And then let me say one more thing about that. And also with the complex roof line, you have more places where leaks can happen because you have more intersections, more places where you're joining different slopes and things. So
there's actually, our house was built in a factory, a modular house. 4 modules were built and then stacked on site. And during the construction, we went to visit the factory, and I took a photo of one of the workers actually putting some flashing where the roof lines met. And he had his supervisor standing over his shoulder on the little step ladder because it was modular. So it was just a little couple feet off the ground, pointing out like how I want you to flash this thing. We actually paid the factory. There was a line item called energy features that was just sort of this bucket of money they could dip into, or they knew that we would be asking for things a little bit out of their normal framework for work. But they did pay attention to it. So that it does require extra effort, a little bit extra cost to get those kind of features there. Some other factors, we really wanted to have a great indoor air quality and low energy costs because we wanted to try to make it net zero. And my current calculations say we will have net zero. And that's because it's all electric too. That was another thing. We didn't just, all these puzzle pieces fit together for us nicely. Having right now, our latest test was a little bit less than 780 CFM50 for around 4,400 square feet of enclosed space. So it running on a 2-ton air source ducted heat pump, even through the winter, even though we had trouble with it. So we could talk about some of the travails and troubles too. So
The personalized performance, then, it makes a lot of sense. You want some things that are going to compromise the building science, the complex roof line, for example. But putting indoor air quality really high is a very good thing. Indoor air quality and comfort are what sell home performance contracts. That's what people are looking for in new homes. A lot of times, the aesthetics, of course, are always there, and however many bedrooms and bathrooms they want, and the 2 sinks in the bathroom, all that kind of stuff is important to people. But the indoor air quality and comfort are 2 of the biggest ones everywhere. When I was in the world of contracting, if somebody called me and had me come out and do an assessment, and their main thing that they were trying to achieve was energy efficiency, I almost never got a good contract out of that. But if they were interested in comfort or concerned about the cough that their daughter had, I had a client like that, that's when I'd get the contracts for encapsulating the attic, encapsulating the crawl space, duct sealing, all kinds of stuff. And those are really important issues that are of great concern to a lot of people.
see, I never knew you did contracting. I think it helps to validate your blog post. They aren't just some guy rambling on. It's coming from experience, personal experience doing things. So I believe you have a little IAQ project going on at your house now. What can you tell us about that?
The first thing to do with IAQ is to make the house tighter. And I've started that process with the attic re-encapsulation that I did. So I made the house more airtight. And we got rid of the natural draft gas water heater. That's a huge thing. Natural draft gas water heater is the cheapest gas water you can buy. It's also the most backdraftable gas appliance in homes. And that means that it's the most likely culprit for putting carbon monoxide in your home. And we got rid of that, put in a heat pump water heater. And then when we got rid of the gas furnace and put in the heat pump for the space heating, we were able to go all electric. So we called the gas company and they came and removed the meter. So we are all electric.
Great. Was there a charge for them to come and pull the meter?
I don't think so. I turned off the gas service and then I had them come out and take the meter away. I don't recall there being a charge for it. But on the indoor air quality, so we also, since the pandemic, whenever we have people over, like my mother-in-law, or very, very small gatherings we've had, a few times we've had them, we have this thing that I call the Comparetto Cube. It's the portable DIY MERV 13 air cleaner that we put together. It's a box fan and 4 MERV 13 filters that sits on the floor, and we turn it on and it filters the air, keeps the PM 2.5 low, and also will filter out most of the virus-laden particles if there are any in the air. So that helps keep things clean and keep us safe. We recently bought an Aware IAQ monitor. I put one in the den, one in the master bedroom. So we're looking at the 5 things that it measures: temperature, relative humidity, which I'm also measuring in other places in other ways, carbon dioxide level, chemicals, which is a whole soup of different things, and PM 2.5, particulate matter 2.5 microns and smaller, very important indoor air pollutants. And I have a Zender ERV, enthalpy recovery ventilator, sitting in my basement waiting to be installed. Got a little project about writing a book that I'm trying to get done. So the ERV probably won't be done for a while, but
Because you're going to install yourself. You will install it yourself.
partly. I did one little bit of installation already. I installed one of the supply vents in a bedroom. I just wanted to see how that would go. I bought myself a hole saw with the little bowl to catch the drywall dust and everything. And it didn't take that long to put that into the ceiling. So that's the only thing I've done so far, though.
So tell us about the book.
The book. So, yeah, it's called A House Needs to Breathe, or Does It? That statement is something I've heard a lot, and I still hear it every once in a while. I get angry emails from people who read one of my articles and say, "You don't know what you're talking about, lady. You shouldn't seal up a house too tight. It's got to breathe." Well, that's absolutely not true. We want houses to be as airtight as possible. We want them to have mechanical ventilation. But we also want to save energy, and we want the house not to rot, and we want to be comfortable. So all these goals matter, and you have to look at the house as a system. So this is an introductory book on building science. And I'm looking at some of these things that people say that are just absolutely wrong, like the house needs to breathe. And air tightness, of course, is one of the biggest things you can do to cover all of the end goals. Air tightness gets you energy efficiency. Air tightness gets you indoor air quality. Air tightness gets you durability because you're not sucking moist air into wall cavities where it can start biology experiment. It gets you comfort because it'll cut out the drafts. And so air tightness is one of the biggest. Choosing that title for the book, I think, is...
It drives the point home. So I picked up, it was at a BPI training session years ago in Long Island. So the presenter talked about controlling expensive air, and I've stolen that line. Because if you care about the air, and then the other thing is in the last year or so, talked about air is a food. It's a nutrient. It's actually part of your biological system that you bring in certain things with it. So we care a lot about the food we eat. We should care about the air we breathe just as much. And we don't know about it as intimately because there's frightfully lack of standards. Maybe you could talk a little bit about standards and air quality, some perspectives from you.
I can do that. But let me say another one. I love the one about controlling expensive air. I'm going to have to use that too. One that I thought of, I don't think I've heard anybody else say this, and I've got it listed in my long list of articles to write someday, and that is air is a bodily fluid.
That goes up against that one about the naked article. What was that?
Yeah, naked people need building science. Yeah. That was a very popular article. I pull that one out again every once in a while. Lloyd Alter, a tree hugger, says that's his favorite article I've ever written. Anyway, so standards, and was there another part to that?
Just the lack of IAQ standards. We have standards for food. We're able to read labels on food, but there's no label for the air that we breathe, that we bring in as a nutrient.
So in homes, there is one standard, and that is ASHRAE 62.2, which is, I don't remember the exact title of it. It's called something like Residential Ventilation for Low-Rise Homes. For indoor air quality is in the title of the standard. I don't remember exactly how it goes now, but the point of that standard, though, is really ventilation. It doesn't address all the other, it addresses some of the aspects of indoor air quality, but it doesn't really address the whole picture of indoor air quality. And when you get into products, we do have standards for some things that work, like filters. Mechanical filters work. Fibrous media air filters work. And ASHRAE has a standard for that, ASHRAE 52.2, which governs the testing required to put a MERV number on a filter. MERV 13 is where you want to be. It goes up to MERV 16. The standard 1-inch fiberglass filter is MERV 2.
And then the MERV stands for minimum
efficiency reporting value. And just that name tells you that this is a standard written by engineers.
Yes. With reporting in it, right?
Minimum efficiency reporting value. Yeah. MERV. So there are some standards related to this stuff, but there's not any kind of overall standard for helping people determine whether they have good indoor air quality or bad indoor air quality. There's also not standards on portable air cleaning devices. There's a whole lot of portable air cleaning devices out there, and some of them there's a lot of snake oil companies out there selling their snake oil disguised as air cleaners, but they don't have to put their product to any test to certain standards like fibrous media air filters do. And they can say pretty much whatever they want. They can do their own testing. They don't have to tell anybody how they did the testing, and they can sell their snake oil. And the general consensus among the researchers and other IAQ pros that I listen to is avoid pretty much all electronic air cleaners. Some of them may work okay, but you can get good indoor air quality by just doing the basic things: air tightness, ventilation, filtration. Do those things, and you can have really good indoor air quality. And also, source control is a really important one. Keep bad stuff out as much as possible. Do local ventilation to get it out of the house where it's generated, in the kitchen especially. So there's just the basic stuff gets us there.
So, and to go bouncing back to my house, now that we've wandered down this one path, we'll draw you back to this one. We have a lot of control over the air movement in the house. Ventilation is done with a conditioning energy recovery ventilator, which actually has a heat pump built into it. And so it runs on command. Either it's not just time. I could set it to run based on CO2 level in the return, the whole house return, or VOC levels, or just on time. And it will also do this recirculate mode to the inventor of it. It's called a Serve 2, conditioning ERV2 by Build Equinox. Ty Newell is the inventor of it. It's got a nice little company out in Illinois, solar powered factory that makes these. He calls it recirculating the stores of fresh air, which is interesting. It's sort of like you've got this fresh air built up in one part of the house, and you may be occupying and doing things in another part of the house. If you can then rebalance it, you're doing your own dilution with your expensive air. That's a really smart ventilation system. What knowledge do you have about the CADR? Because there is some standard out there for clean air delivery rate. What is that about? Do you know more about that?
I know only a little about that. So if you're using a portable air cleaner, which could be like the Comparetto cube that I mentioned earlier, which is, I should mention, the Comparetto cube is a variation of the Corsi Rosenthal cube, or portable air cleaner, which was 5 filters and a box fan. And the reason for 4 or 5 filters is to lower the pressure drop across the filters. You get better airflow, and you can run it on low instead of high and still get good airflow and get a better clean air delivery rate. Clean air delivery rate is the airflow rate times the filtration efficiency. And it's a way of telling you how well you're cleaning up the air in a room or in an indoor space. So, just like with ventilation, we measure it in air changes per hour. And clean air delivery rate is also, you can convert it to air changes per hour. So you could do it in CFM or air changes per hour, I believe. It's a combination of the airflow rate and the filtering efficiency.
We're going to jump to another topic here of something that's actually in my house too. This conditioning ERV has MERV 13 filters in it for the ventilation air, both on the incoming airstream and on the recirculating airstream. So it picks up what we generate inside as well as what's coming in from outside in the ventilation air. But they recently introduced late last fall a UV lamp for this device. And UV lamps have come under a lot of scrutiny, especially from, I think, knowledgeable people are questioning the application of them and what they're actually designed to do. I was a little bit skeptical, but when I saw it was backed by Ty Newell, who's an ASHRAE legend, and the white paper that they wrote about it, it sits in a reflecting chamber, the stainless steel chamber. So the UV has a chance, the rays have a chance to really bathe the air that's moving through it. And it's got a fairly low CFM rate. It isn't the main HVAC system for the house. In fact, I say I have an HAC and a V. I have 2 systems. So I was pretty confident when I saw, and I bought one and installed it, and my system was retrofittable into the Serve 2. So now it's a Serve 2 plus UV to treat anything that's in the air. But can you riff on UV lamps a little bit, please?
I can. Yeah, I wrote an article about that last year. And this is one of the things that a lot of companies are selling to homeowners to improve their indoor air quality. And they may or may not be getting their money's worth when they do that, because the installation. So first of all, ultraviolet germicidal irradiation, UVGI, can work. It can kill viruses, it can kill algae, and it can work very well in HVAC systems. But there's a number of things that have to be done properly.
Yeah, things have to stack up.
Yeah. Number one, it has to be sized appropriately for the airflow. Like you were just mentioning the low airflow in your Serve 2. If you put in a UV system and it's relatively small and you've got a high airflow rate, the UV is not going to do a whole lot. It might catch some of the stuff whizzing through there, but a lot of it's just going to pass right through. So it has to have the right power intensity for the airflow.
To irradiate and to do something to upset something inside the virus to cause it to deactivate or something like that. It's actually, you don't kill viruses, right? I understand. I've learned that somewhere else. I've got to check that against your physics knowledge. You don't actually kill viruses, you deactivate them.
Yeah, I guess so.
Because they're not alive.
Yeah, they're not really life forms in the traditional sense. Yeah. And that's a little bit out of my bailiwick, but
okay.
Bill Bonfleth, who's a ASHRAE guy from Pennsylvania, Penn State, is a really smart guy. And the article I wrote last year was based partly on a webinar that I said in that he did on UVGI. And it's a technology that works well for healthcare facilities, where they can do things like upper room UVGI, where they irradiate the air at the top of the room. The thing about UV is You don't want the UV to hit people. Well, UV comes in different wavelengths, and you want the short wavelength, high energy part of the UV spectrum, because that's the part that gets filtered out by our atmosphere. So we don't get that down here. It's UVC. And the UV that we get is UVA and B, and I think UVB is the one that causes sunburn. So UVC is what you want, but you don't want it hitting anybody. So upper room UVGI can work well. UV inside a duct system can work well, as I mentioned, if it's the right power intensity, and also if it's not hitting the filter, because filters degrade when exposed to UV, inside induct UV like that. So that has to be part of the design. And I guess those are the two main things. It needs to be the right power, not hit the UV, and not hit the filter. It can also, in addition to deactivating viruses, it can kill algae growing on the coil in a drain pan. So that's an issue with a lot of air conditioning systems, especially in humid climates in the eastern part of the country where we are.
And the algae is stationary on the coil. That's an important distinction versus things moving through the air. You can't catch them fast enough with the wavelength unless it's properly sized with the flow rate and the power level. But if it's something sitting still, you can beam on it for an infinite amount of time to take care of and deactivate the things that are growing on it. So it does make sense, but to extend its capabilities without engineering is bad.
I knew there was a third thing about UV that you have to be careful of. There are some UV systems out there that generate ozone. You don't want ozone being generated by your UV light because ozone is bad for humans. So we don't want that in indoor air. I think it's OSHA has a limit of, I believe, 5 parts per billion.
Yeah, very low.
Of ozone in the air. That's a really low limit. Anything more than that is considered a health hazard. So make sure that if you do go the UV lights route, that you get one that does not make ozone.
Right. Do you want to shift into another IAQ topic of a device that I don't have in my house, but creates ozone? Do you know the 4-letter acronym we might be talking about here?
A device that you do not have in your house that creates ozone?
The 4-letter acronym, which is being used a lot in the industry now.
NBPI?
Yeah.
Yes, needlepoint bipolar ionization. This is one of those devices that I talked about earlier that manufacturers can make up their own story about it. They can make up their own name. So one company might call it needlepoint bipolar ionization. Another company calls it bipolar ionization, but they're basically the same thing. And some of these devices create ozone. Some of these companies say they don't create ozone, but when somebody else tests them, they find lots of ozone created by them. So don't just take the manufacturer's word for that on these things. And I've got an article coming out about electronic air cleaners this week. I spoke with Marwa Zatari, who's been one of the loudest voices on this issue. Just recently came across her. Man, she's powerful voice on the topic of electronic air cleaners in general. So I've got an article on that coming out this week.
I'll put Marwa's name in the show notes for those of you that didn't pick it up because I want to make sure I spell it correctly. But she's all over Twitter.
And LinkedIn too.
Oh, LinkedIn too. Okay. I'm going to jump back to a topic about my house, which was one of the personalized performance features that we were really interested in was mean radiant temperature. And I think that goes back to your Naked People article, doesn't it?
It does, yes.
Yeah. This was influenced by Robert Bean in part, and also by you in part, just understanding that if you don't have the walls and the windows sucking away heat from your body or adding heat to your body, you just feel more comfortable and you effectively get more usable space. That's the other aspect that Robert talks about. What are some of the challenges of achieving mean radiant temperature from either physics or builder standpoint, your view?
It's a really difficult challenge in really cold climates because you've got, if it's minus 40 outside, and at minus 40, we don't have to say what temperature scale we're talking about because that's where Fahrenheit and Celsius cross.
Intersection, yes.
So we can just call that minus 40 FC, and the FC could stand for anything you want there. In a really cold climate, it takes a lot of insulation and air sealing to keep the inner surfaces at a comfortable temperature in the middle of winter. So that's one of the challenges. The other is even in milder climates, it's the same thing to a smaller degree. You want, when we talk about mean radiant temperature, and let's define that a little bit here. Mean radiant temperature is the average temperature. Mean is another word for average, and it's the average temperature of all the surfaces around you in a room. So if you're standing in a room and you got a floor beneath you and 4 walls around you and a ceiling above you and you got windows, all those surfaces have temperatures. If you've got one exterior wall, it looks like the room you're sitting in might have one exterior wall, Bill, and maybe a window. So the interior walls are going to be pretty much the same temperature as the indoor conditions, but the exterior wall is going to depend on how much insulation you have, how well air sealed it is, and the window temperature will depend on what quality window you put in. Is it double pane, single pane, triple pane? Does it have any low E coatings? And is it in the direct sun? So you've got all these factors that come into play. With the mean radiant temperature, that one exterior wall is going to be the determining factor for your comfort, and the window. The window more likely, because the window is not as good as the wall, almost always. Well, always, I could say. Well, okay, in older houses, if you have an old house with uninsulated walls and you change the windows from single pane to triple pane without doing anything to the walls, you can have a better window than wall, but that would be stupid.
Yeah, a little bit silly there. Jumping to another topic which relates to our all-electric home and our shared properties of heat pump, water heater, heat pump space heating, which we both did. And the topic, do you talk much about exergy?
No, I don't do exergy.
You don't do exergy.
That's a Robert Bean thing. He's the comfort and exergy guy, thermal comfort and exergy.
My real surface level understanding of exergy is you create heat as close as possible, or thermal energy as close as possible to the temperature you wish to use it at is the most efficient way. And he's got this graph. I should probably put a link in it looks like a whale's tail. Do you remember that whale graph?
Vaguely.
Yeah, it's pretty cool. Okay, we'll get Robert on to talk about exergy. But you had something to comment?
I will say something about that. I believe it's basically based on Carnot's theorem about the maximum theoretical efficiency of heat engines and heat pumps. And the temperature difference is the determining factor for both of those. For heat engines, the Carnot efficiency is based on the temperature difference between them, and the bigger the temperature difference, the more efficient the heat engine will be. For a heat pump or a refrigerator, it's the reverse. You'll get the highest Carnot efficiency when the temperatures are very close together. And think about the heat pump in your house, for example. You're going to be able to pump a lot of heat from outside very efficiently when it's 55 degrees outside, and a lot less heat and less efficiently when it's 15 degrees outside. The smaller the temperature difference between inside and outside, the more efficient that heat pump and the more capacity it will have. I think that's basically where exergy is coming from.
You did an article recently about a cold climate heat pump from a industry icon.
Yes.
I'll talk about that a little bit.
The industry icon is Gary Nelson, the founder of the Energy Conservatory, maker of the Minneapolis blower door and the Minneapolis duct blaster, two essential devices for testing air leakage and duct leakage. He has been an icon, is a good word for it, in the industry for decades now. And he lives in Minneapolis, as you might suspect, from the name of his company and his products, the Minneapolis blower door, Minneapolis duct blaster. I visited his house about 2 years ago, I think it was, 3 years ago. He had recently done a remodel, made the house much more efficient, put in triple pane windows with 2 low E coatings, and did some really good stuff. The air leakage is really low. He's got really good insulation levels. The load, I don't remember the size of the house. I think it's about 2,500 square feet, maybe 3,000 at the most.
Yeah.
And the load on this house, the heating load on this house is 18,000 BTUs per hour.
Wow.
Let me say that again. For any HVAC people who know loads, this is a house in Minneapolis, 2,500 to 3,000 square feet, and the heating load is 18,000 BTUs per hour.
Now that's design load for Climate Zone 6?
I believe it's Climate Zone 6, yeah.
Close, if not.
That's not that's not so much his design load, that's his observed load, which he based on his previous heating system. He did the calculations for so on a design day, when they were at their design temperature, which is, I don't know, 3 Fahrenheit or something like that.
Yeah, probably.
It's
under
pretty
5.
low.
Yeah.
So he looked at how much heat the system was producing on a design day, and it was about 18,000 BTUs per hour. He put in a Fujitsu heat pump that provides about 18,000 BTUs per hour at design conditions. But they have had weather below that. In the article I wrote about some weather they had a couple years ago where the temperature went down to minus 27. He was out of town at the time, actually in Australia, where it was summertime. But the house, they weren't there. The house got down to 59 degrees, so no danger of pipes bursting or anything, and the house was fine. He said if they had been home, they could have baked some cookies and their body heat probably would have kept it warm. The next year, they did, or maybe this was the year after. There was one year with an update he sent me. They had some cold weather again, and they had to do a little bit more than baking cookies. He said he put the oven at 350 and left it open for a while. And let me point out, this is an electric oven, so not a gas oven. You would not do this with a gas oven. He had an electric oven, so it's basically auxiliary heat in the kitchen. He opened the oven for, I don't know, an hour, and then he closed it and left it on 350 for the rest of the day. So it was cycling on and off. And all that heat from the oven was going into the house. And he also has some standalone space heaters, 1,500 watts each, that he can use when he needs it. So he does have extra auxiliary heat, but it's outside the system, not built into the system.
Other appliances, very cool. So jumping back to my high performance, personalized performance house, one of the factors, we actually looked at a passive house concept and had a passive house architect to do a starting design, but we decided that there was a diminishing return to the increasing level of insulation to sort of achieve the passive house level, the standard. And we were more about moving in, getting the house, building the house to our other parameters, the aesthetics, the space, that kind of thing, the functionality. So we backed away from the passive house concept, but we did include exterior insulation, but was only 1.5 inches thick. So we could avoid adding a rain screen before we put on the cladding. That saved another expense and a step because you can't secure things into foam. Why don't you talk a little bit about thermal connection to outside, to outdoors?
Okay, let me first ask you a question, though.
Sure.
You were going down the passive house route for a little while, and then you changed, but you still did some good stuff with the building enclosure.
Yep.
This February in Texas, a lot of people lost power. And one interesting thing that happened during that time was a bunch of the passive house folks on Twitter started this thing called the Passive House Challenge. I don't know if you saw that. An architect from the UK named Mark Sidal, I don't know how he pronounces his last name, but he started this. And the challenge was for anybody who wanted to participate, you could do it whether you had a passive house or not, was to turn off the heat in your house, turn off the space heating system, and monitor the indoor conditions and report indoor and outdoor conditions for your house every day. And a bunch of people participated in this. John Simmelhack, who you've had on the podcast before, was one of those people. The closer your house is to passive house standards with all the insulation and airtightness that requires, the more resilient your house and the longer you can go. So did you participate in that?
No, I missed it. But Dale Sherman?
Yeah.
From New York State. I was looking at trying to quantify the energy use or just sort of get a block load of the house as installed. I mean, there was the Manual J. We actually did a passive house planning package on the proposed design, but then their as installed, of course, is different. He suggested picking a very cold night and then shutting everything off and then just watching the temperature drop basically and see how long it would take. So I would probably do it when we're not home because 2 reasons, perhaps the discomfort, but also just getting in and out. We're going to upset the conditions, the experimental conditions.
But by leaving, you're upsetting the experimental conditions too, because you're not adding your body heat and your activities to using appliances adds heat to the house, cooking. You've changed the experiment that way too. It was a really cool thing that happened. And when I get my house in better shape, I would like to try that sometime. When we have near design conditions in Atlanta, our winter design temperature is 23 Fahrenheit. So I'd like to, my wife might need to either be away or not know about this.
Yeah.
Until she discovers what's going on. But yeah, I'd like to see how long it would take my house to become uncomfortable. Right now, I think it wouldn't take very long.
We have a south-facing view. We have most of the glass. I don't know what the percentage is, but a lot of the wall area is glass. We're actually getting blinds put in the next week or so because even in March, there were some really sunny days when it was 20 degrees outside and 80 degrees in the house and the heat pump wasn't running. We were getting so much thermal gain that it was starting to get uncomfortable. You could wear shorts. The floors are warm and everything like that. So tailoring that performance to what we like, you just can't, we aren't totally interested in all that solar gain.
Yep. I gave a talk at a energy code workshop in Aspen, Colorado a few years ago. And One of the people who was there was an HVAC contractor, and he came up to me during the break and told me there are houses in Aspen where in the wintertime, people run their air conditioners because they've got the big glass facing south so that they can see the slopes. And so all that sun is coming in and overheating the house. And they could just open windows and have an economizer or something to bring outdoor air in. But he says he has to install systems that are able to do low ambient cooling so that they can run their air conditioner in January or February. But the point you talked about was in March, and that's more common, where in March and the spring and fall, the sun is still relatively low in the sky. So those windows can get a lot of solar gain. And if you've got a really good building enclosure, that sun's bringing the heat in, it can overheat. That's been a problem with some passive houses.
Yeah. We took the passive house concept of eliminating thermal breaks with the 1.5 inch extruded or expanded polystyrene, EPS.
EPS is expanded.
Expanded polystyrene that was actually graphite impregnated, I believe.
Oh, good. Yeah.
Yeah. So it has this interesting characteristic where the R value goes up as the temperature goes down, the test temperature goes down.
That's true of most insulations, actually.
Oh, really?
Not just the graphite impregnated EPS.
They promote it very well. It caught my eye.
Yeah. I was wondering which kind you use on the outside, because if you had used 1.5 inches of polyisocyanurate, that might not have been so good because polyiso has a problem of the gases condensing in the cells when it gets really cold, and that increases conduction through the insulation. So unlike most insulations, which increase in R value as it gets colder, at a certain point, polyiso will drop in R value because of that condensation happening in the cells. So with 1.5 inches, you would lose a lot of R value that way. If you're putting 6 inches of polyiso on, it would mostly be in the outer part, because once you get to that 4th and 5th and 6th inch of polyiso, the temperature is going to be closer to the indoor temperature. It'll be warmer and may not hit that dew point for the gases.
The gases to accumulate. Interesting. I enjoyed the conversation. Any closing thoughts or questions for me?
Gosh, no, I can't think of any right now, but I'm glad you're in your house. I remember you posting about designing the house and asking me questions at some point and thinking about going passive house and looking at all the options. The Serve 2, I didn't get a chance to say much about the Serve 2. We've done some design jobs for people with the Serve 2. I don't have direct experience with it, but I hear it's a really good system. And also, Martin Holliday wrote an article a few years ago in Green Building Advisor about a researcher in Vermont who looked at carbon dioxide levels in homes and in relation to the type of ventilation system they had. And the Serve 2 came out on top.
Yeah, that's one of the studies they have on their website. They talk about that, the Vermont. It's Vermod. I think it was modular housing also. VERMOD study.
It could be, yeah, I don't remember that part.
Yeah. All right. I'm going to give the listeners their ears back, and I want to make sure that people stay aware of the book that will be coming out, A House Needs to Breathe. I'll put a link to Energy Vanguard blog, which is probably the best place to contact and connect with what Allison's thinking and doing. And if you need any consulting services for training, consulting, HVAC, he's out there to help.
Also, let me say one thing about the book. On our website, if you go to the blog, there's some ads at the top of the blog and other places where you can click and get updates about the book. So you can see the update page, and you can also put your email address in there and sign up for the email updates that I send out every once in a while.
Excellent. Enjoyed seeing you. It's been a while since we've seen each other in person. It's good to see you on the screen here as we're recording. Hope we can get back to physical meetings with people here shortly.
Yeah, me too.
Well, thanks for coming on the Building HVAC Science podcast, Allison.
You're welcome. It's been a pleasure, Bill.
Well, thanks for listening to this episode with Allison Bailes, investigating. The Energy Vanguard investigates. Got a lot of other great resources out there in the internet world, different trade-oriented podcasts and resources like the HVACR School, Service Business Mastery, Tool Pros, Zach Ciota on Shop Talk, HVAC Reefer Guy, Grayson Corbett Lunsford at HomeDiagnosis.tv, and of course all the great stuff. You'll see Jim Bergman popping up everywhere like whack-a-mole, talking about Measure Quick and all kinds of things IAQ related. Real fun stuff. I also host the Res Talk podcast. You might find some crossover information there. Res Talk, just RESTALK. Search for that in your podcast app. Here's a thought for today by Paulo Coelho. When you're enthusiastic about what you do, you feel this positive energy. It's very simple. Hopefully, on this topic about energy, home energy, etc., and performance and construction, you feel the energy that I'm trying to exude here, and you get engaged and think differently about it. That's the whole point of this, for me at least. If you're in the market for tools or test instruments related or mentioned in our podcast, look at my company. I'm co-owner of TrueTechTools.com, TrueTechTools.com. You can also use a code HVACBS, that's HVAC Building Science, HVACBS, for a nice discount. The Building HVAC Science podcast is a production of True Tech Tools, and we appreciate your listenership. Please like us or rate us or follow us. Just do something, okay? Promise? When you get off this podcast, you're going to like us? All right. Thanks a lot, and I hope you listen in again to the Building HVAC Science podcast. Take care.